everybody. So I'm happy to have the opportunity to talk. I'm actually in here from Seattle, so it's my first time at EmpireDAO. So I'm really glad to have the opportunity and great to see the attendance. I think people already kind of covered a lot of stuff I'm going to cover, but I'm going to cover some of it in more depth. So my background, so I'm more of a programming languages, compilers person. I got into blockchain about a little bit over a year ago. I worked on compilers for Java, C#, C++, frameworks for compilers, things like C, extensions to make it safe. But I was really interested in correctness and security, and so blockchain was like the space to go. Let's see. So in this talk, what I'm going to do, and I'll try to get out of the way of my own slides here. If the camera is pointing this way, so I can go.
No, but see that, it's fine.
Okay.
Oh, fine.
So if you look at Move and Solidity, this was just pointed out, so both of these languages, I'm going to cover where they're similar and where they're different. So the first thing is, these are domain-specific languages for smart contracts. This was just pointed out by the previous speakers. That means that you can really specialize things and try to make things as good as possible for programming smart contracts. So they have different programming models for managing on-chain storage. This is alluded to by previous speakers. If I get through just that, I think that'll be great. And then I'm going to go into some comparisons. As been noted by previous speakers, Move is really inspired by Rust. So it really borrows heavily, and the pun is intended, from Rust. Solidity was more inspired by C. So I'm just going to sort of cruise through what's different about the type systems. And then if I have time, I'll get into some of the syntactic differences, just so when you read a Move code, it'll make it a little easier, a little bit of a crib sheet. And finally, I'll talk a bit about the formal verification that Move supports. So, okay, let me move forward. All right, so as you all know, a blockchain is really a distributed ledger. So it's a distributed ledger along with the transaction history. So in a blockchain, you have a mapping from addresses to data or something like that. I'm sure all of you guys know that. And so for Solidity, you have two kinds of addresses. You have an externally owned address, all right, and that's basically like a user who has money on Ethereum, and then got the balance. Or you've got a contract address that has a balance, but it has two other things that come with it. It has code and data storage. Now, your externally owned address, as you know, is controlled by a private key. The contract address is controlled by code. So now if you look at Move, things are organized a little differently. You have an address, it maps to an authentication key. For every address, there's a possibility of data storage. So it's different than an externally owned address on Ethereum in that there is a data storage that has something called resources. The prior speakers talked about what that is. I'll get into some more detail. And the idea is that most accounts should only have data. You have some accounts that will have code. The code is stored in something called modules. But the idea is most accounts should only have data. Data can include resources that represent items of value. So resources, in particular, the items of value should be stored in the account that owns that item of value. And so it's not stored with the code. And so the key point is the data in storage can represent an item in value, and the items of value should be stored with those accounts. And this is what gives Aptos the ability to have really high throughput. Because basically you're saying your data is separate, so the data, you can access the data without, if two accounts are talking to each other, it doesn't matter what any other account is doing. That transaction can complete independent of any other accounts. And so here's a nice picture that I've got here, which I just grabbed from the internet. So this is Move versus Solidity. So the key thing is if you're writing a Solidity code, you typically have a mapping that says, hey, this address has this value here. So you have this hash table mapping, it is a hash table, but it's a mapping. And so what you end up with here is you have global storage, and then you have the contract address, and then within the contract address, you have the balances here. So this tells you for every account, for every user, who owns this thing. Okay, and then, okay, so now we get to Move, things are different. So Move 2 has global storage. This is the ledger. Okay, and then you have addresses here, and you have different addresses here. Well, like this address, hex ABC here, it owns a coin. And the coin is directly in the storage for that address. And over here, this thing owns a coin too. You have another address, it owns a module, so it owns some code, happens to own some data, but the point is when you're implementing the smart contract, you shouldn't be putting the data in with where the code is going. You should go over here to these other other accounts. And that's really what's key to enabling Aptos. It's key insight that I think will enable the high throughput that Aptos has. So, okay. So let's jump into the language comparison. As people have mentioned, Move is inspired by Rust. Solidity was inspired more by C. So Move uses data to directly represent the items of value. So what this means is that ownership is important. So once you determine that ownership is important, this is why you want to sort of try to use what Rust has done, try to do something based on Rust. Ownership is a key concept in Rust. Ownership is about how you manage memory in Rust. It's a key built-in concept. So I'm going to go over the types, and then I'll go over the syntactic differences between the languages. So this is a little boring. These are just built-in primitive types. This is what I want people to know. So Solidity has unsigned integers, signed integers, booleans, addresses, fixed size addresses. Move here, you've got U8, U64, U28. So you only have unsigned integers. You don't have signed integers. You have booleans, you have addresses. The prior speakers covered signers, their capabilities that give you the power to act on behalf of an address. And then there's some stuff that Solidity built in, like fixed sized and variable sized byte arrays, that they weren't strictly necessary. But Solidity the theory was really the first. They were worried about efficiency. And so in Move, they simplified things and just used constructed types. So there are additional types here. So Solidity has fixed size and global arrays. If you're programming in Move, you've got vector of T. So it's a global array of type T. And you can shrink these things too. In Solidity, you have a map. In Move, you don't need map. It can be made available as a library. There's enough fundamentals in Move that you can just build it in. One important thing is that Move has this notion of references. And they're sort of pointers, there's a slight typo inside, pointers of sort of to values. So if you've ever programmed in C++, you might have seen these things. So you have address of T here, which says this points to like a T struct here, struct of type T, but it's immutable. So you can read the data, but you can't write it. And then you have address mut T, which is really, that's a mutable pointer to T. And these things aren't full pointers. You can't do address arithmetic or anything funny like that. Basically, it points to an object of type T, and you can either read at the object or you could read and write the object. And so, let's keep going. So, when you look at struct types, this is really where the differences start to show up here. So, if you look at struct types here, in Move, you say you store them in fields here. So, the idea is you have, here's two struct S's. They've got an int64 value and an address. So syntax looks pretty similar here. Here you declare it using the identifier followed by the type. There you declare it using the type followed by the identifier. The key point is that in Solidity, a struct is a reference type. So a struct is actually means it's a pointer to something that's in memory already. In Move, a struct is a value type. So if you actually want to create a reference type, you actually have to construct that explicitly. And I have a nice diagram to show this here. So, so suppose this is global storage here, and this is very simplified, very abstract here. You've got an instance of struct S. So you've got an instance of struct S living somewhere in your global storage. It's got the UN64 and the address here. So that is actually the value type here. And you can have references that point to the location of something in storage here. So, in Solidity, if you use a variable, and the rules are a little complex and I can do all of them, use a variable in Solidity, basically you get a reference to memory or a reference to storage for the most part. So this indirection is happening automatically as part of Solidity. If you use Move, you actually have to create a reference that points to this value that's been stored in memory somewhere. So that's a really key difference. And the reason you want to have that difference is it lets you talk about ownership. Who owns that blob of data in memory? So let's see. So this is an example. I think I can skip through this. Basically, the structs in Move, they can be any type except references. And the structs have Rust-like linear typing. And the interesting thing is the default is that a value of a struct type cannot be copied or destroyed. So, if you have a value stored in a struct type, you can't copy or destroy it by default, unless you grant the capability as the programmer to let that happen. It can, however, by default be moved around. I think that's kind of probably where the name comes from. And so the idea is you have this notion of type abilities. These are inspired by Rust. So the abilities are control what actions you can take for a given type. So in other words, there's 4 abilities that that Move gives you. There's copy, which says the value can be copied or cloned. So typical examples, you might expect somebody to be able to copy an integer. What you don't want them to do is copy a coin. That's bad news. Drop says, the value can be dropped at the end of the scope. So again, if it was an integer, it's fine if you got a scope, your variable ends. Store says this value of this type can be stored inside other structs in global storage. So this basically is saying you can put this thing in global storage. And a key says you can use this value as use this type as a key for global storage operations. So that's actually a bit of a type. It should be type. Let's see. All right, so I think we're a little short on time, but basically, if you have a type ability here.
You have time. You have time.
I find? Okay, good.
Yeah.
If you have a type ability here, it's declared as part of a struct type declaration. So you don't have to add it, but if you don't add it, then you just get the default behavior here, which is no copy or drop ability by default. All right, and so if you have this function here, we have this function can't copy t. It takes in a reference to t here, and now somebody tries to dereference the reference star x here. Well, that would make a copy. What you're going to get is invalid dereference. Dereference requires the copy ability. You're going to get an error here. All right, and similarly, if you try to drop a value, you take a struct in x of type t here, and you just fetch the value out of it here. It just has a single field here, x.b. X drops out of scope and is destroyed. So you get this unused value without drop. So in other words, you accidentally lost something. The drop ability prevents you from losing a coin. If you want to fix this, what you can do is, if you want to fix the can't copy thing, you say struct t, well, it has the copy ability. And if you want to fix the drop, when you add it, it's saying it has the copy and drop. So what is a resource then? So now you've got the basics on like what a struct type is. A resource is a struct that only has key and store abilities. And this is taken from the Move book. It's kind of more of a convention here. The key thing to know, this is really important, is an account can hold at most one resource of a type. Okay? So if you have an account, you have a coin, your account can hold one copy of that coin. Now, when you have the coin there, what you do is you store the balance in the coin. So you have exactly one copy of that struct type in your account. And so because of the constraints put on resources, you can't copy or drop it. It's impossible to accidentally lose points. Okay, and so the question is like, how do you get things in and out of here? One of the other presenters put this chart of operations up here. So the key thing is, so let's look at borrowed global T here. So this here, it sort of returns an immutable reference to these T stored under an address. It's the address associated with T. There's a single instance of T here. So this is when you say this borrowed global T, it goes to the address and says, oh, is there a reference of type T at this thing? And it goes and fetches it out. Okay, and so it's sort of interesting that there's a lookup based on the type of the resource here. And then you have other things here, which is you have the ability to create something. So you create a copy of the struct locally, and then you do this move to here. You have to have a signer permission. So you have all these different operations here that allow you to manage resources. And again, because each account has one copy of the resource, this gives you independence if you're trying to execute lots of transactions in parallel. So if you're trying to do this in Solidity, you'd have a lookup table, you'd have a hash table. Hash tables don't always parallelize that well. So it would, that's why you end up with a slower transaction rate there. So, okay, so anyway, that's the key concept for like what are resources about in Move here. So let's see. I'll take like one or two questions if anybody's confused about this point. And this is like key to understanding solidity versus move. And if you want to hold the question to the end, that's fine, or find me afterwards, that's also fine. But if you have any questions about what I just said, I'm happy to answer them.
Anyone? Yep. There we go. 1 second.
So again, this is somewhat from ignorance because I haven't played around with Move yet, but we talk about the 4 different types of capabilities in Move. I guess maybe so for a token you talked about like the 2 that are there. What about for other types of assets like NFTs or the equivalent of something like a sold out token? Do they tend to use like a similar?
They would use the similar
capabilities.
A similar set of capabilities. So for an NFT, maybe you're a little less worried about people copying it, but usually you would if you're but maybe you want to give out the ability to use the NFT for a certain period of time. But they would use the similar capabilities. But you can, if you decide that the capabilities are getting your way, you can also hack around them if you need to.
Nuance? Not then we.
Okay, I'll keep going. So now I'm just going to talk about some of the syntactic differences between Solidity and Move. And this is just like, I always like to be able to read the code and understand the code. So here, and this is very much a Rust-inspired thing. If you want to declare a variable, you say let identifier :type equals E. And the type annotation and initializer are optional. The compiler actually tried to infer the type for you here. So you like say let A equals 0. And even though on the other side of the example of a UN64, the compiler may not infer that A is actually a UN64 here. You may have to write 0U64 here. But if you want to be absolutely certain that A is a U64, you could actually just declare the type here. And on Solidity, you just have UN64. And then you have this notion of storage. Where is this thing living? Is it in storage on the blockchain or is it in memory here? And that is the difference there. So the use of let is Rust inspired. And then there are syntactic differences around expressions and statements. So Solidity is inspired by C, so it has statements and expressions. So for example, expressions are things like arithmetic, shift operations, functional call, assignment, etc. Statements are things like control flow, if, while, for, break. Move only actually has expressions, interestingly enough. So you can have an if expression, and both sides of the if have to evaluate to the same type. And similarly, you have like a while expression. There's a programming language person like, okay, it's a little different, but it works fine. While and for loops evaluate the unit type, which is just something that has basically no value in it. And so, so you will find differences when you go to program. You have to be aware of this distinction here. And then finally, functions here. You have functions. In both cases, the syntax doesn't actually match. Well, in one case, the syntax definitely doesn't match C, which is here you declare a function, you say the ID, a parameter list returns. Here you write fun, ID, parameter list, and then you can have a return type. And I left off, there's other additional annotations. One of the things that one of the prior speakers mentioned is that you have to declare, if somebody's going to take ownership or use a resource, you have to declare this requires thing, which sort of gives you an idea of what type is this function actually using. Okay, so that was my very quick summary of the difference in syntax that you're going to see. Now I'm going to talk a little bit about formal verification. So I'm from Certik. Certik was founded by 2 professors, one from Yale and one who's now a professor at Columbia. These guys are really into formal verification. They were the creators of Certik, which is the world's first and only fully verified multi-core OS kernel and hypervisor. They won a whole bunch of awards. I think the Certik work has won 3 Amazon Research Awards. What I can say is it was a big breakthrough in the ability to formally prove and reason about real systems. And so we are, let's see, so there's an example. It was deployed at a UAV here, but it's not too relevant for blockchain. So what is formal verification about? Formal verification checks that code satisfies a specification. And so it's like testing, and it's guaranteed to hold in all cases. And so there's no runtime or compile time overhead. Now, this sounds like maybe too good to be true. The answer is you can't always formally verify things. You can try to do it automatically. You can try to add annotations, but in general, it's an undecidable problem. You can't always do it, but when it works, it's great. So Solidity provides what they call the SMT checker. So the SMT checker treats required clauses as preconditions. It tries to prove that your cert clauses will never fail. There are people actively working on this, actively working on improving this. Move has something called the Move prover. And the key thing to understand about Move is it has a richer specification language. So just to give you an example here, a simple example, if you have a function double here, which takes US64 and adds them together, you might have a specification that says, actually, this ensures that the result of this function is x times 2. So you're taking advantage of the fact that you know x plus x is mathematically equivalent to x times 2. Obviously, this is a very simple property. You can do much more complex properties. So the thing to know about the Rust specification language is the specifications, first of all, it has the specification language built into the language. So that's like the first thing. And we're working on a blog post about how to make use of this at Certik, so hopefully we'll have that done in a couple of weeks. The specifications are, we've been playing with it internally, but we want to create a nice tutorial for people. The specifications are separated into spec blocks. The specifications specify 3 things. They specify what the failure conditions are. They specify preconditions, requires, like before you call this function, this must be true. And they specify post-conditions. And so this has a sophisticated language support for verification as things like for all exists. So for example, you can write something that basically captures what max does mathematically. So if you call this max function on an array of values, it would tell you that the value come back has to be larger than anything in the array. So, how does this all work? I could spend tons of time on this, but the Move prover translates the specifications into logical expressions. It passes them off to SMT solvers. These things are like names are like Boogie, Z3, CDC5, and they either come back with one of 3 results. They come back with true, like this is true. They come back with a timeout, saying we ran out of time, we couldn't prove this. So they come back with a counterexample that there's something wrong. And this is really exciting because we have done a ton of work at Certik on like verification of like ERC20 contracts and Solidity. And so to see this kind of stuff built into the language, it's exciting. We have to do like a ton of work. This is kind of built in to Move, so it's pretty cool. So anyway, with that, thank you for listening. Thank you for coming tonight. I think I have time for a few questions.
First of all, a round of applause. That was a wonderful presentation. Thank you very much. And also thanks to our speakers who were here previously. So let's take a few questions.
Sure.
Hi, thanks so much for the presentation. Wondering if you're familiar with the language Ink. It's used for substrate chains.
Yeah, I'm not familiar with Ink.
Okay. I've never thought to ask a question before, but I thought I don't know if you'll answer it, but so Ink is a Rust-based language for building on the substrate ecosystem.
Yes.
And they call themselves an embedded domain-specific language. So that means that it's embedded into Rust as a language. And in comparison, Move, they are not embedded into Rust, but they are inspired by Rust.
Yes.
So I kind of just came to this realization, but I'm not too sure. Like, I don't have enough experience to understand why anybody, what are the considerations one would make when deciding to build a DSL between embedding it into a host language versus completely creating a new language.
Yeah, I mean, usually the question will come down to: is there an ease of programming? Can you simplify things? So it's like there's certain things you could write certain kind of code in like C, but it'd be like much easier to write it in Java, or it might be much easier to write that same code in Python. So one consideration that comes up is ease of use. So in particular, a general purpose language can have lots of features in it that maybe are a little bit sharp edge. My background, if you've used C++, you know what I'm talking about. Some of these features can be hard to understand. So one is ease of use. The other one, though, is you can really specialize the programming model here. So here, what they've been able to do is elevate the management of blockchain state to a really first-class concept in the language. And so, and then that gives you additional properties because now, because the programming model is a little specialized there. I talked about how you have a resource and there's exactly a resource as a type, and then one instance of a resource for an account. That lets you do things like now you can parallelize things. You have two accounts that are independent of each other, two accounts, operations involving two sets of accounts that are independent of each other. They shouldn't conflict. And so that gives you some advantages. So that's really always what it comes down to. It's the same thing that inspired them to create Solidity to start with, was that same set of decisions.
Okay, awesome.
Thank you. Great question.
Anyone else?
Okay, well, I'll be around after, I think we have a little bit of social time after this. I'll be around to talk with people. And thank you again.
Another round of applause.